In this problem, we are having to write an equation for a growth or decay, exponential growth or decay problem, and then actually solve it for some specific value. So let's take a look at what these look like. This one says a culture of 5,000 bacteria is placed in a petri dish and begins to grow at a rate proportional to the culture's size. Those are our key words to know that we have a differential equation here. In general, the rate at which something grows, dy dt, is going to be proportional, some constant, times the amount of stuff that's there, times the function itself. So that's our general differential equation for this situation. In this case, they're telling us that k equals 0.045. So here we want to write the differential equation first. Well, dy dt equals 0.045 times y, and that's all we need there. And then the initial condition. What is the initial condition? Well, in this case, it says we have 5,000 bacteria and it begins to grow. So this is our starting point. So y of 0, where x equals 0, or t, sorry, where t time is 0, we have 5,000 bacteria in there. Okay, so now we're getting pretty far along here. Let's continue on. It says find the particular solution to the differential equation that satisfies the initial condition and write your answer in the form of y equals some function, where all the terms involving t are on the right-hand side, and use exact values in the answer, not decimal approximations. Okay, we can do that. We can do that. What we know we have to do is write that differential equation and then go ahead and solve it for y by integrating both sides. So our equation, as we've already said, is dy dt equals 0.045 y, whoops, y. And then we want to get all the t's and dt's on one side and y's and dy's on the other side. So I'm going to divide both sides by y, and I'm going to multiply both sides by dt. So I'm going to get um, uh, 1 over y dy equals 0.045 dt. When it's in this form, I can go ahead and integrate, and we're going to get the natural log of the absolute value of y over here, and we're going to get 0.045 t, this is a function of t, plus a constant here. We're going to exponentiate now, and we're going to get the absolute value of y equals e to the 0.045 t plus c. This plus c, you can think of that as, when you add exponents, you're multiplying the basis. So this is e to the 0.045 t times e to the c, and that e to the c is just a constant because e is a constant and so is the c. So that can be brought out front as a big constant, and then we call this c times 0.045, or to the 0.045 t power. I dropped the absolute value because this population is growing, so we're not going to look at the negative side of this equation. So there is our general formula. We need to find out what c is, though, and we actually already know. It says the initial condition y of 0, that's where t is 0. If you multiply 0 by this power up here, it's going to be the power of 0. E to the 0 is 1, so c has to equal 5,000. If you plug in 0 for t, you get 5,000 out here for c, because y equals 5,000 at time 0. So now our equation is y equals 5,000 times e to the 0.045 t power. Okay, so that is the general answer here. Then C says how many bacteria in the culture after 7 hours. So the way you're going to do that is just plug in 7 in here for T. So Y is going to equal 5,000 times e to the, let's see, well, I'll write that out, 0.045 times 7 power. And that is, well, that is e to the 0.315, and we're going to multiply that by 5,000. Just doing this on my calculator here. And does it want to, yeah, nearest whole number? I am getting You can verify this on your own. I'm getting 6,851 point a little bit. That's our nearest whole number. So we have 6,851 bacteria after 7 hours. So that's a little more work with using these differential equations for modeling growth and decay.